Section 3.1, linear models. This first problem, you had a problem like this on the test, and we looked at some of those back in chapter 1. We'll go over this one. He asked a question at the end that we didn't talk about, so let's talk about that. Growth and decay. This is a growth model. It becomes a decay model if there's a negative in front of that K. So this is a growth. The population of the town grows at a rate proportional to the population present at time t. They're using X to denote here the population. What I'd probably do is just go back and just call it P. dP of dt is equal to K times P. The initial population of 50 increases by 15% in 10 years. What will be the population in 30 years? So I'm going to use dP over dt is equal to some constant times P, or P of t, if you will. Separate the variables and solve for this. You recall, once you solve this, this is P of t is equal to some constant times e to the kt. Everybody remember that? How to go from that derivative, that differential equation, this guy, to produce here this population growth function. This is the initial population. That is that when the time is 0, the population is equal to 500. And then it says in 10 years, the population grows by 15%. So when t is equal to 10 years, the population at 10 is equal to 500 plus 500 times 0.15. That is, P of 10 is equal to 575. So we can use the initial part here when t is equal to 0, P is equal to 500, there to solve for capital C. So we have 500 is equal to C times e to the k times 0 for the time. Well, that implies that C is equal to 500. Thus, P of t is equal to 500 times e to the kt. Now that second condition, when t is 10, P of 10 is equal to 575. We use that to solve for k. So we have 575 is equal to the 500 times e to the k times t, or here the t is 10, so 10 times k. Solve for k. We're going to divide both sides by the 500. Is equal to e to the 10k. Take the natural log of both sides. So we have the natural log of 575 over 500 is equal to 10 times k. Well, this implies that k is equal to this natural log of 575 over 500 it's all over 10. On your calculator, that's a really small decimal, 0.01396. And so the formula P of t is equal to that 500 times e to the kt, and k is this decimal. You got to be very careful with that because that decimal is always cutting off part of the answer, and so this is 0.01. So I try to write for me as many of those significant digits as I can to try to make sure that I'm getting close as possible to the true answer. And that's times t. So it says, what's the population in 10 years? I'm sorry, 30 years. We found 10. What's the population in 30 years? So P of 30 is equal to 500 times e to that 0.013976 times 30. So on your calculator, it comes out to be about 760. It's like 760 with some change on that, but I'm just doing the approximation, 760. And this is population of some town, so just people. Yes, sir. Yes, sir. What's 15% of 500? It's 75, but the population would be 500 plus 75. Yep. So then the next question that it asks, this is pretty cool. It says, how fast is the population growing at t equal to 30? How fast is the population growing at in 30 years? What would you say? How would you respond to that? Yes, sir. I love this class. I love this class all over again. Yes. When it says how fast is something going, that's the derivative, right? That's the rate. It's very good. Matter of fact, that's the P of t, or D of t over dp. So check this out. So it says how fast is the population growing in 30 years? Well, it is dp over dt at t equal to 30. So just look at that. dp over dt is already given to be the constant times the population, right? So the population at 30. So that constant is that 0.013976, and then times P of 30, you found that to be 760. So it's like 10.6 something, so they're talking about just people, so we're going to just say 11 people per year is how the rate, is growing. So it's about 11 people per year, which is pretty cool because if you notice that differential equation, that's what's given initially, right? That the population is growing with respect to some type of constant times the population at the present time. So hopefully, that it makes the equation make sense. And I had one student that asked me that, and I thought that was pretty good. He said, look, it's one thing to solve these problems, but it's good and it's better if you can kind of apply it to something so then these numbers, these variables kind of make more sense then, okay? So that's why I thought it necessary for us to talk about more of these problems in Chapter 3 because they're application problems, okay? Any questions about that one? Okay. Well, let's look at, I'm going to skip number 4. It's very direct. I went over something like that before. I'm going to try to work some problems that have not done before. So this problem down here, number 4, is you can find that. I went over that one. Number 13, I did that one as well. Now, I didn't do one of these, so let's look at a mixture problem. A large tank is filled to capacity with 500 gallons of pure water. Brine containing 2 pounds of salt per gallon is pumped into the tank at a rate of 5 gallons per minute. The well-mixed solution is pumped out at the same rate. Find the number, the amount here of pounds of salt in the tank at time t. So here, the amount of salt is being pumped in at some rate. So here we have this dA of dt. I want to be able to find the amount of salt at some time t. It's going to equal to the rate of salt that's being pumped in minus the rate of salt that's being pumped out. So we have this difference between the input and the output. So we got some tank. And here we're pumping this brine in, this mixture, this water solution of salt being pumped in. But then you also have that salt content being pumped out. So here it says that this tank has a capacity of 500 gallons of water. The brine containing 2 pounds of salt per gallon is pumped into the tank here. So it's being pumped in at 2 pounds per gallon. It says it's pumped into the tank at a rate. So the rate in, let's say R sub 1, is 5 gallons per minute. The well-mixed solution is pumped out at the same rate. So here, R sub 2 is equal to this 5 gallons per minute. Now let's look at the rate in versus the rate that's coming out. So the rate of the salt that's coming in is going to be this 2 pounds per gallon times this rate here, the 5 gallons per minute. Need to make sure that we end with the rate, because that's what we're looking at. So the gallons here cancel out. So I have some type of quantity divided by time, so that's a rate. So here we have 10 pounds per minute of the rate of the salt that's being pumped in. Let's look at the rate of the salt going out. So here, now, the rate that's going in, they tell us that we have 2 pounds of salt per gallon going in. They don't tell us that for what's going out. So here we're going to call that A. That is basically what we're looking for. Find the number, the amount of salt per pound, of pounds of salt in the tank. So here this is going to be A. Since it's in pounds, all I do know is that it's coming out of a 500-gallon tank. So here, the weight of the substance there is going to be 500 gallons. I do know the rate that's going out. That's 5 gallons per minute. We want to make sure that the rate in, the rate out, that the units are consistent. Right? The units are consistent. So here, I need to end up with the rate of the salt out in terms of pounds per minute as well. So here, the gallons cancel, and we have that 5 divided by 500 is going to be 100 downstairs. So this is sum A, which is in pounds, divided by here 100 minutes. So we can write that in that differential equation. Well, the differential equation says that I have dA over dt is equal to the rate in, just use that, talking about salt, so the rate in minus the rate that's going out. This dA over dt is equal to that rate that's in, that's 10 pounds per minute, minus the rate that's out is the amount which is in pounds all over 100 minutes. So I'm just going to just use this. This is just shorthand notation. dA over dt is equal to 10 minus A all over 100. We'll just use that. Okay. We solve that guy. Now, I'm going to write it like this to see if you see, because understand that in chapter 2, the goal was to develop all of these models by which, if I have an application, I can apply the application to the model that it fits, right? I'm going to write this in a form that you've seen before, and then you tell me how to solve it from there. This is dA over dt plus 1 over 100 times A is equal to 10. What form is that? Mm-hmm. Linear. Man, for a guy who didn't take the test, man, you're doing pretty good, Travis. This is linear. So since it's linear, then we need the integrating factor, right? We call that mu is equal to e to the integral of this 1 over 100. Here, this is with respect to t, so 1 over 100 dt. So I get e to the t all over 100. The left side, we said, is automatically the derivative of the product here with respect to time the product of the integrating factor e to the t over 100 times the dependent variable, which is a, that's equal to that right side times the integrating factor, 10 times e to the t over 100. Integrating both sides, integrate that derivative we have left, just e to the t over 100 times a, that's equal to 10 times the integral of e to the t over 100 dt. What's the integral of e to the t over 100? What's the integral? Yes, sir. Gosh, you took the thing on test, man. I don't understand. You're able to answer all my questions. But anyway, yes, you see that the integral of e to the t over 100 is 100 times e to the t over 100. Let u equal to t over 100. du becomes the dt over 100, so 100 du is dt. Right? So that's where we get the 100 factor. So if I put it here, this implies the left side is e to the t over 100 times a is equal to 10 times that 100 times e to the t over 100 plus a constant. So here a of t is equal to 1000 times e to the t over 100 plus c. Now, how much salt is in this tank initially? It's pure water. So the amount of salt in there is what? 0. So a of 0 is equal to 0. You want to be able to solve for c. Right? So if a of 0 is equal to 0, so the amount of salt is 0 in the initial times e to the, here t is 0, so we replace that t with 0. Plus c. Well, that implies that c is equal to negative 1000. Right. We call it the limiting factor. So a of t is equal to, here, that 1000 times e to the t over 100 minus 1000. And so now you can take this formula, and at any time t, you can find the amount of salt in that tank. And that's all it asks for, right? Find the number, a of t, of pounds of salt in the tank at any time t. Right? So like my question on the test is that I can give you this problem, then I'll say how much salt is in the tank at 10 minutes. Right? Well, I'll stop there. There were, I think, 2 more problems that I'll work when you come back from this section, and then we'll move on to the next section. Thank you. You can keep the test.